Good morning, everyone. So, hope you have revised yesterday's topics. This is continuation of yesterday's topics, and we are going to finish this chapter today. All right. After that, I'll revise. But anyway, as I promised, I'll finish alternating currents also before we go before the school reopens. Okay, right. So, I'll give you a quick review of what we learned yesterday. We were on self-inductance and mutual inductance, right? Self-inductance. Okay, I'll tell you what it is. It's a very simple concept. We have a coil. This coil is also called a solenoid. Okay, it can be a coil or a solenoid. You have a pipe over which a coil is wound. All right, a wire is wound. And you connect it to a cell and a switch like this. This is a cell and a switch. And what happens now? Imagine you are switching it on. When you switch it on, what's happening? When you switch it on, the current slowly picks up. The current starts increasing, right? Current does not become maximum all of a sudden. Current steadily increases to become maximum, right? Current increases. It becomes constant likewise. Got it? Okay. So current increases like that. And then automatically the magnetic field inside solenoid, magnetic field also increases. Correct? Okay, because current is causing the magnetic field. Obviously, current increasing would mean that the magnetic field is also increasing. Okay, then what? Magnetic field increases means, in technical terms, we would call it flux. Flux increases, right? Flux increases. Field lines would keep increasing, so flux also will increase. And what happens when you switch it off? If you break the circuit, what happens? The reverse will happen, right? The reverse. What about that? Tell me, Bilal. Current would decrease, right? Magnetic field will decrease. Flux will decrease. Even if you missed yesterday, you will understand. Don't worry. It's on me. So both ways, you can see that there is a change happening, right? Change. What kind of change? The flux is either increasing or decreasing. Flux is in general changing. Okay. And according to Faraday, when such a situation comes, an EMF should be developed. Okay, voltage should be developed. Flux change always results in the generation of an EMF. This EMF is called self-induced EMF. The phenomenon is called self-induction. Okay, self-induction and self-induced EMF. We even wrote an equation for this. Flux is given by L into I. What is L called? L is called self-inductance. A resistor has a resistance. A resistor will always have a resistance. Capacitor has a capacitance. Similar way, when you have an inductor, it is said to have an inductance. It is also called coefficient of self-induction. Coefficient of self-induction or self-inductance of a coil. Got it? Okay. Self-inductance of a coil, which is denoted by the letter L. And again, you know, the unit of L is Henry. If you remember, Henry is the unit of self-inductance. And the second equation we learned is equal to minus L into di by dt. L into di by dt, EMF generated. I told you that an EMF will be generated, right? And that EMF is called self-induced EMF, sometimes called back EMF. Why back EMF? Because it opposes the cause. Do you remember Lenz's law? Anyway, I'll come back to that. We learned it before vacations. Lenz's law states that this EMF always opposes the cause. We even did a lot of questions on it. But anyway, just know that Lenz's law states what? It always opposes the cause. Something is happening, that will be opposed. That will be opposed. That is what Lenz's law says. Correct. Whatever is happening will be opposed. That EMF will oppose the cause. That is why you see a negative sign here. Correct. Hope you remember this, what you saw there. I'll show you. Actually, you saw this once, but I'll just show you one more time. You seem to have forgotten it. Now, this is the demonstration of Lenz's law.
Lenz's law as the no, you don't law.
You remember this?
Whatever you try to do, nature acts to oppose.
In fact, he is trying to press it down, the sheet, but it is in a magnetic field. What happens then? As it goes down, there is an EMF developed, a current developed, which will oppose the cause. The cause is him trying to push it down, but that will be opposed, right? Correct. So see what's happening?
There you go. If
It's very difficult to push it down.
Currents are induced to slow.
You face a resistance, right? Look at that. It's very difficult.
But if you try to pick
On
up
the other hand, if you try to pick it up, that's again difficult. Why?
nature also says, no, you don't.
Why?
In this case.
Because again, as you try to pull it up, again a change of flux happens, an EMF is developed that will oppose the cause. Causes him trying to pull it up. Okay, so that also will be opposed. So basically, whatever changes trying to happen will be opposed. Got it? That is what Lenz's law says. Okay, we learned it already. We learned it already. That is it.
The plate, attracting it back to the magnet.
It's drawn like bull.
Okay,
No matter
so
how hard I tried to push the plate down,
so let me ask you one question in that case. So let us put it this way. Imagine you have a switch. All right. Any switch, no? Any electrical switch you have. Maybe the switch of refrigerator or air conditioner or whatever it is, washing machine, a high power electrical device. When you switch it off, what you're doing is you are breaking the circuit. Correct. See, when you switching it off means what? You're breaking the circuit, right? Correct. Correct.
Yes.
See, there was a circuit, there was a contact. Now, when you switch it off, the contact is broken. Contact is broken means current will decrease. Current decreases means what? Field decreases. Field decreases means what? Flux decreases. Flux decreases means what? EMF will be developed. Right? That EMF should oppose the cause, right? Oppose the cause, right? The cause here is breaking the circuit. It can't actually re-establish the circuit. Instead, it will send a spark across the switch. Send a spark across. This is why now when you're home today, just try looking into the switch. When you switch it off, you can see a spark inside. That is why, because it is trying to re-establish the contact. That is as per Lenz's law. Got it? So again, this is a previous question. Why do we see sparks in switches when you switch it off? It's a previous board question. They might not give this in school, but it is important. When you switch it off, you are breaking the circuit. So the current decreases, field decreases, flux decreases, and EMF is developed. That EMF should oppose the reason, the cause, right? The cause is breaking the circuit will be re-established. How? By sending a spark across the switch. Okay, this is also self-induction. It is due to self-induction. Self-induction is also called inertia. I didn't tell you yesterday. I was about to tell you today. Inertia of electricity. Inertia means what? Inertia means laziness. In simple common man's language, inertia means laziness. When you are trying to switch it off, it is lazy. Lazy for what? Lazy to be switched off. Got it? See, imagine you are switching it off. It is resisting, right? It doesn't want to be switched off. Lenz's law opposes it, right? When you try to switch it on, again that is opposed. That is why it is called inertia of electricity. Whatever, because see, when I say I have inertia of job, what does it mean? I like this job, I'm comfortable with this job, I don't want to switch my job, right? So I have laziness. I have basically inability to switch my job. Same way, the current has inertia. Inertia means it doesn't want to change its state. Got it? Current, see, circuit does not want to switch on. The circuit does not want to switch off. Got it? I can show you. Look at this. This. I think you saw this, the spark in switch. Once I gave all the videos in the last class, I think, last class. Look at this. That's a huge electrical circuit, a high powered circuit with a huge solenoid. These are two solenoids. And then what happens? See what happens when it is switched off? That is switched on now. Switched on. Did you see the spark? The spark is so huge because it's such a high power device. Okay. But you know, like I said, you can see small sparks inside your switches at home. Okay, every electrical power switches will have a small spark inside. It is basically due to self-inductance or inertia. Got it? Self-inductance of inertia or inertia of electricity. Got it? So this is self-inductance. What about mutual inductance? How about mutual inductance? Yesterday we learned in place of one coil, we got two coils side by side, right? One coil right here, right? Shape lesson, please. Right, second coil. Second coil is what? Second coil has a galvanometer. Correct. Tell me what's happening. Tell me, Josh. When you switch it on, where do you switch it on? Primary or secondary? Primary. So primary current will increase. Correct. Primary field will increase. So primary flux will increase. So secondary flux will increase. Because a part of primary flux is shared to the secondary, right? Is given to the secondary, right? Okay. So automatically, similar way, when you switch it off, what's happening? IP decreases. Correct? Yes, BP decreases. So flux in primary decreases. Flux in the secondary also decreases. As you can see, there is change, right? So EMF is developed. This phenomenon is called mutual induction. And the EMF is called mutual induced EMF. Okay. And here also we have equations. Phi S is equal to MIP. S means secondary, P means primary. Remember, your teacher might be using phi 2 and MI1, 1 and 2 in place of P and S. Got it? That's just fine, no problem. Okay. And another equation is EMF in the secondary is minus M into dIP by dt. M is called what? Coefficient of mutual induction or mutual inductance. You know, these equations are similar. Look at that. Here, flux is L into I. Flux is L into I. L is called what? L is called what? Self-inductance. Say it again. L is called self-inductance. And EMF is minus L into di by dt. Here it is mutual inductance. Phi S is equal to MIP and ES is equal to minus M into dIP by dt. Got it? dIP by dt. Got it? All right. So this is all about the introduction. I'll have a quick recap one more time. Look at this. Yesterday we learned about self-induction. Self-induction. We have a single coil to which you attach a cell and a switch. Whenever there is a change of current, there will be change of field, there will be change of flux. Consequently, an EMF is generated. Correct. This phenomenon is called self-induction. Try to get the idea and write on your own. Do not learn things by heart, okay? Right. And this results in EMF and the flux is L into I. EMF is minus L into di by dt. Okay. And secondly, the spark in switches. Yesterday I didn't tell you, but I'll write it today. When you switch it off, the circuit is broken, current decreases, field decreases, flux decreases, EMF is generated. That EMF tries to bring the contact back. All right, by giving a spark. All right, spark is due to self-induction. All right, it's also called inertia of electricity. Inertia of electricity. Inertia means laziness. Laziness or the tendency to remain in the current state or tendency to maintain status quo. All right. Okay, the current state. When you're trying to switch it on, no, it doesn't want. And when you're trying to switch it off, that is also not possible. Got it? Anything is opposed. Anything is, it is trying to oppose whatever you're trying to do. Got it? That is called self-inductance, inertia. And then I told you about mutual inductance. The only difference is we got two coils instead of one coil. Self-inductance and mutual inductance. Got it? Got it? It's called inertia of electricity because it always resists the change. It always shows resistance to the change. Got it? Doesn't want to change. It doesn't like the idea of changing. Got it? And that is why it is called inertia of electricity. Okay? And I'll tell you one more thing today. Look at this. This is an important question. Many times this has come in examinations, and it is one of the most important questions in BPS papers. Because all the time they ask this question, it's a previous board question also. It's given as an example question on the reader. Imagine yesterday we did coaxial solenoid. I'm going to do a coil here. This is a big coil. Right inside, I got a small coil. Okay. I call the radius of this one as R1 and this one as R2. Okay. This one is R1, this one is R2. The inner one, please. The inner one carries a current I1 and the outer one carries a current I2. All right. Okay. We did two derivations yesterday. For those who missed, I don't have time to repeat it, but that is an independent topic. You won't have any problem. All right. Anyway, I'm going to find out mutual inductance of a pair of coaxial coils. Okay, and this is usually asked in Birla schools only. It's an example question, it's important for boards anyway. Okay, right, we got two coils. One of them is called primary, the other is called secondary. Never mind, textbook has taken them 1 and 2. Got it. So I'm going as per the textbook this time. Okay, right. So first of all, I'm going to write flux. How to write flux in the first one? I can write the flux as B into A. Flux in the first one is, so don't write now, I'll give you time. Flux is given by what? Do you remember this? Don't you remember? Flux is given by what? Tell me. Electric flux is given by E into A, or it is E into ds. This is from Gauss's law. Do you remember? So magnetic flux, yesterday I told you it is B into A. Magnetic flux is B into A. Look at that. Magnetic flux is B into A. And flux in the first one, I write the flux in the first one as B1 into A1. I made a mistake. You know, I take it as B2 into A1. Why B2 into A1? Because this is sitting in the field of who? One of the coils actually sits in the field of the other one, right? Correct. See, you are trying to find the flux of what? This coil, flux of this coil, right? Flux of this coil, right? And that is sitting where? Inside the magnetic field of the outer coil. Am I correct? Am I correct? I'll tell you, don't worry. So this is B2 into A1. Magnetic field due to a circular coil. I don't know if you remember or not. Magnetic field due to a circular coil. We learned it in the last chapter. For the time being, just see this. This is how I wrote it. Mu 0 by 4 pi, I by R into 2 pi. Magnetic field due to a circular coil is mu 0 by 4 pi into I by R into 2 pi. 2 pi cut, mu 0 I by 2R. So I am writing it here. Mu 0 I2 divided by 2 R2. And this is area of the first one. Area of the first one is what? Pi R1 square. Area is pi R square, right? No, tell me, it is circular area. What is it? It is pi R1 square, right? Circular area is pi R1 square. So tell me what you get now. I got phi 1. My idea is to get the amount of M. How to get M? Get this I2 to denominator. That's it. Now see the textbook. See how complicated it is in the textbook. Okay, it's very simple. Once you got the idea, it's very simple. If you read textbook, it is totally messed up there. That's what. Okay, so M will be what? M will be phi 1 divided by I2. What is phi 1? We just found it over there. Mu 0 I2 by 2R2 into pi R1 square divided by I2. I2 cut. Finally, we have the answer. What is the answer? Mu 0 pi R1 square by 2R2. Got it? Got it? It's just okay even if you interchange ones and twos everywhere. No problem. You can use them invariably. Got it? If you try with phi 2, what would you write? Phi 2 is equal to B1 into A2. Got it? You can just interchange 1 and 2. There is nothing wrong about it. Got it? Mutual inductance of, that proof is no more there. Mutual inductance of first coil with respect to second is same as mutual inductance of second coil with respect to first. That proof used to be there like 5 years back, but it is deleted now. Got it? M12 is equal to M2. Show that M12 is equal to M2. That's no more there in syllabus. Got it? Okay. Now this is the 3-mark question. It's very, very important. Coefficient of mutual induction for a pair of coils. Got it? Got it. Don't worry, we'll do it again. Okay, one more point. Okay, so one more point, we'll come back and write. Now look at this. This is what? You know, the laboratory equipments, no? Have you seen a laboratory resistance box?
Yes.
Have you been to your school laboratory? Yes. So there is this resistance box where you just plug the keys out, right? To get the required resistance. But if you open the back side, you can see a lot of coils being wound like this. Why do they wind the coil? That is how they make the resistance. Understood? You may need like 1 kilometer of wire to make, say, 1000 ohm resistance. But can you have a box of 1 kilometer length? No, it has to be compact, right? Yes. Oh, no. See, in order to make the resistance, the only possibility is to have a wire. And you have to keep it in the wound form, right? Wound form, so as to make it compact. But what is the problem? Now it is a solenoid. It has induction, right? That will actually affect all the readings. So what will they do? They will wind it backwards like this. so that induction due to one coil will be cancelled by the induction due to second coil. They are anti-clockwise with respect to each other. Understood? Against each other, right? So the induction effects will be cancelled. Understood? You will get a perfect resistance. Got it? And this is called non-inductive winding. Non-inductive winding. No inductance. Understood? Because inductance is an undesired effect. Got it? That will actually slow down the measurements. Got it? So that part is also there, not there, but this is important. Why do we have what is the relevance of non-inductive winding? Non-inductive winding. What is non-inductive winding? In standard laboratory resistance boxes, if you open the back side, you can see the coils. The coils provide the resistance. Okay. But what I want is pure resistance, right? What is the problem? When you wind it in a coil, it always gives induction, electromagnetic induction. Correct? Induction effects are not needed at all. You don't need them. Got it? What we need is what? Pure resistance for the coil. Got it? So how can we achieve this? Just by winding one coil. When you're done winding, stop there and wind it in the reverse direction. Got it? So that induction due to one coil will be nullified by the other coil. This is called non-inductive winding. Got it? We got only two more points left. One is AC generator. Second is energy stored in an inductor. Chapter is finished. Okay. So let us start. Start writing. All of you online understood this? Everyone? Okay. So you can write recap. First is what? First concept is self-induction. Self-induction. Something we learned yesterday, right? Self-induction. Self-induction. Okay. Draw the figure. Solenoid to which you connect a cell and a switch. Solenoid to which you are connecting a cell and a switch. Self-induction. So just tell me what's happening? Current increases, right? When you switch it on, current increases, right? Current increases. You must have learned it by now because I've said 100 times at least. Okay. Current increases, magnetic field also increases, flux also increases. On the other hand, when you switch it off, current decreases, field decreases, flux decreases. We learned all these things yesterday. Okay. So when you switch it on or off, you see a change, right? All right, Bala. Thank you, Jeffin. Yeah. Okay. So in both cases, EMF will be developed. EMF means electromotive force, also called voltage. Okay. Electromotive force or voltage. You are creating a voltage. That's it. Okay. Electromotive force. This is called self-induction. Let us just write the equations also. Phi is equal to Li. Don't ask me where I took them from because we learned it yesterday. Learned this yesterday. Put them in a box. These are the equations you learned yesterday. Flux is given by L into I. And EMF is given by minus L into di by dt. EMF is given by minus L into di by dt. Okay. EMF is given by minus L into di by dt. All right. All right. So this is self-induction. Self-induction is on a single coil, right? Single coil, it is called self-induction. And two coils, it is called mutual induction. Mutual. Got it? Right. So write the next one. Write the next one. Mutual induction. The only difference is that this time you have two coils, Adarsh. That's it. Cell and a switch. And in the secondary, you will have a galvanometer. Primary and secondary. So where is the current given? Current is given in the primary. Where do you see the changes? In the secondary. Right. For something that's happening in primary, you see the effect on secondary. Right. Hope you got it. Adarsh. primary current is changing. You're switching it on. The moment you turn it on, current starts picking up, right? Current starts increasing, right? Okay. So you can write on, primary current increases. When primary current increases, primary field increases. There is a magnetic field inside primary. Automatically, primary flux increases. So secondary flux also increases. Now switching it off, primary current decreases. Primary field decreases. Primary flux decreases. Secondary flux decreases. Either way, there will be an EMF. This phenomenon is called mutual induction. And let us write the equations here. Phi S is equal to MIP. Finished. dIP by dt. Okay. All right. So write this. Write not number. Oh, sorry. This is primary flux. Okay. Tell me when done. So let us write the question. Write it as important. Okay. Find an expression for, right? Find an expression for mutual inductance of a pair of coaxial coils. It's an NCERT example question. Write it here, 2025 March. It's going to be sure. Find an 3-mark question. Find an expression for mutual inductance of a pair of coaxial coils. Coaxial solenoid we did yesterday. This is coaxial coils. Okay. You can use the notations primary and secondary, but I'm using 1 and 2 as per the textbook. Okay. So just draw the figure. We got like a big coil right inside a small one. Okay. And the inner one has a radius R1, outer one has a radius R2. The current on the inner one is I1. The current on the outer one is I2. These are called coaxial coils, circular coils. Okay. And if they say N turns, you have to put an N also, NBA, like we did yesterday. But in the textbook, they have taken only 1 turn. Okay. Keep it as such, only 1 turn. Finished? Okay. Consider a circular, consider 2 circular coils. Consider 2 circular coils. Consider 2 circular coils of radii R1 and R2. Consider 2 circular coils of radii R1 and R2. Consider 2 circular coils of radii R1 and R2. and carrying currents I1 and I2. Consider two circular coils of radii R1 and R2 and carrying currents I1 and I2. Okay, I1 and I2. Full stop. Next line, flux linked with the smaller coil is. I prefer to take the smaller coil because textbook has given so. Okay, you can take the other one also, no problem. Flux linked with the smaller coil is Smaller coil is 1, right? Correct. The bigger one is 2. Smaller coil is 1. I have named it as 1, R1, I1. Correct. The bigger one is R2, I2. Correct. Okay. So flux linked with, what did I write? The smaller coil is, you can write phi 1 is equal to, you may have a tendency to write B1. Never do it. It is what? B2. Because primary is sitting in the magnetic field of secondary. Secondary is sitting in the magnetic field of primary. Correct. So when you take the flux of first coil, take the magnetic field of second coil. Got it? The bigger coil is creating a magnetic field. And actually the inner coil is situated inside that magnetic field. Am I correct? Okay, right. So write it now. Phi 1 is equal to B2 into A1. On the margin, you write this magnetic field due to a circular coil. You learned it in the last chapter. I'm writing it somewhere here. Magnetic field due to a coil. B is equal to mu 0 I by 2R. Where do we get this from? Don't ask me. Where do we get this from? This is from last chapter, right? Magnetic field due to a circular coil is mu 0 I by 2R. Correct. So I'm putting it right into this. Mu 0, tell me what? I2 divided by 2R2. Why 2's everywhere? Because I'm finding magnetic field of 2. Correct. I repeat one more time. Magnetic flux linked with first coil. Magnetic flux linked with first coil is equal to magnetic field of second coil into area of the first coil. Correct. What is magnetic field? Magnetic field of a coil, I have written over here. Magnetic field of a coil is what? It is learnt already, mu 0 I by 2R. It is second, number suffix is 2. So mu 0 I2 by 2R. Correct. What about area of the first coil? Look at the shaded area. Area is pi r square, right? Pi r1 square. Correct. Pi r1, radius of smaller one is r1, right? Area of a circle is pi r square, isn't it? That's a smaller circle. So pi r1 square. Correct. All right. So the magnetic field is more or less same here, constant here. So tiny in comparison with the big coil. Okay, in comparison with the bigger coil, this coil is so tiny. The magnetic field is more or less uniform. Okay, right. So let us complete this. So I can write it one more time. You can keep it this way, no problem. Therefore, write this. Phi 1 is equal to Mi2, isn't it? Phi 1 is equal to Mi2, isn't it? Let us put this as equation number 1 and this as equation number 2. So I've gotten two equations for flux. I'm going to compare them. That's it. You can substitute or compare. That's it. This is phi 1. This is also phi 1. Then equate them. Comparing 1 and 2. Tell me, Akhil. Comparing 1 and 2. Right. Just substitute. Mi2 is equal to mu 0 I2 by 2R2 into pi R1 square. Cut the common terms out. I2 and I2 are cut. Finally, you are left with M is equal to mu 0 pi R1 square divided by 2R2. This is a reader example question. It's very, very important. Okay. Mutual inductance is mu 0 pi R1 square divided by 2R2. Sorry, all along I made a mistake. It's not coaxial. Coaxial is given for cylinders. This is concentric. Concentric. Make the correction everywhere. Coaxial has to be changed to concentric. Concentric means what? Concentric, same center, right? Both the coils have same center. Okay. Concentric. Okay. Concentric. Okay. So let's have a quick recap here. We have like two concentric coils. Concentric. Okay. So you got two coils. One coil at the center, another one around this. Got it. Two coils. One of them can be called primary, the other can be called secondary. But here they haven't used primary and secondary. Instead, on the textbook, they have put 1 and 2. Got it. So the inner radius is R1. Inner coil has radius R1. Current I1. Outer one has radius R2 and current I2. Got it. And I'm going to find the flux linked with the first coil. Phi 1 is equal to, flux was written as B into A yesterday, or even before that we learned it. Flux is equal to B into A. So flux in the first coil is phi 1 is equal to B2 into A1. Why B2? Because first coil is situated inside the magnetic field of second coil. Okay, so magnetic field is that of second coil. What is magnetic field's equation? Coil's magnetic field, we learned it before. Mu 0 I by 2R. Say it again. Mu 0 I by 2R. Correct. I'm putting it here. Mu 0 I2 by 2R2. Why 2? Because it's all 2 right here, right? And area of circle is pi R square. This is circular coil, right? They'll give you circle. This is a standard question. Circular coil only. Got it? Pi R square. Pi R1 square. Okay. And then what? Flux is also given by Mi. We learned it yesterday. Flux is given by, flux in secondary is mutual inductance into current in primary. So, flux in the first coil is mutual inductance into current in the second coil. So, you got two equations for phi. You can compare them. Mi2 is equal to mu 0 I2 by 2R2 into pi R1 square. I2s are getting cut. Eventually, you are left with mu 0 pi R1 square divided by 2R2. Hope you got it. Clear? It's a 3-mark question. It's very important. You have to learn it today itself. Okay. Right. So let us write a couple of notes. Note number 1. Note number 1. Self-inductance is called inertia of electricity. Why? Inertia means, like I told you, the resistance to change. Self-inductance is called inertia of electricity. Why? Self-inductance is called inertia of electricity. Why? Okay. Why? Because when there is growth of current, see, growth of current, growth of field, growth of flux, EMF will be generated. It will oppose the cause. The cause is growth, right? Oh no. Tell me, I'll show another experiment. Okay. So growth of current. When there is growth of current, there will be growth of field. There will be growth of flux. There will be EMF, which will oppose the cause. Cause is growth of current, right? Correct. I repeat. You know, when you switch it on, what happens? Current will increase. Field will increase. Flux will increase. EMF will be developed. According to Lenz, that EMF should oppose the cause. Who is the cause? Growth of current, right? Correct. So the growth should get delayed. Growth actually happens very slowly. Understood? Growth happens very slowly. Similar way, what happens when you switch it off? Tell me, current decreases, field decreases, flux decreases, EMF is developed. EMF opposes the cause. Decay of current, that is opposed. Decay becomes slowed down. Got it? So in effect, when there is growth of current, there is opposition. When there is decay of current, then also there is opposition. Got it? That is why we call it inertia of electricity. Got it? Got it? So you can write, when there is growth or decay of current, self-inductance when there is growth or decay of current, self-inductance opposes it. When there is growth or decay of current, self-inductance, it's called. When there is growth or decay of current, self-inductance opposes it. When there is growth of current, it is opposed. When there is decay of current, it is also opposed. Correct? Okay. By Lenz's law. This is why when there is growth or decay of current, comma, growth or decay means death. When there is growth or decay of current, comma, self-inductance opposes it by Lenz's law. This is why, it's a previous board question. This is why self-inductance is called inertia of electricity. Self-inductance is called inertia of electricity. This is why self-inductance is called inertia of electricity. Got it? Inertia. Electricity actually is lazy. Lazy to be turned off, lazy to be turned on. Okay. Number 2, not number 2. Spark in switches. Spark in switches. You saw this in a video now. How does it happen? You turn it off, current is dropping. Correct. Current is breaking, right? You can write switched off. What happens? Current decreases, right? I'm not writing in full sentence, I don't have time. Okay. When you switch something off, current decreases, right? Current decreases means what? Field decreases. Because when you switch a circuit off, you are breaking it. Look at that, you are breaking it. Look at this, you are breaking this. All right, the path is broken. Current is dropping, right? Correct. The current is dropping. So current decreases, field decreases, flux decreases, EMF is developed. Correct. EMF is developed. That EMF opposes the cause. Okay. So see the sequence. You can just visualize it. Now, when you're trying to switch it off, the current is dropping, the field is decaying, flux is decreasing, automatically EMF is developed. That EMF will oppose the cause. Correct. The cause is current decreasing, right? So it has to re-establish the contact, right? So you can write circuit is re-established. The broken contact is to be put back, right? The broken contact, this is the broken contact, there will be a spark. Okay. The broken contact is re-established by a spark. This is why you see the spark only when switching off, not when switching on. Okay. Sparks are seen when switched off, circuits are switched off. Spark in switch, switched off, current decreases, field decreases, flux decreases, EMF is developed. Opposes the current, circuit is re-established by a spark. Okay. By a spark. Got it? Not number 3. You finished this, all of you? Not number 3. Right. So write this non-inductive winding. Non-inductive winding. Draw the figure. A coil wound once, it is wound in the opposite order, right? You're winding it this way, and once you're done, you're winding it backwards. Got it? Non-inductive winding. No induction, non-inductive winding. Winding is, see, induction is such an undesired effect here. We don't want it, right? What I want is pure resistance, right? Okay. Non-inductive winding, write this. In standard laboratory resistance boxes, in standard laboratory resistance boxes, in order to eliminate, what I want is pure resistance only. But the problem is when you wind it, automatically something happens, right? An induction comes, right? You have to get rid of it, right? Correct? In standard laboratory resistance boxes, the same resistance box you use in laboratory, school laboratory. Okay. In standard laboratory resistance boxes, in standard laboratory resistance boxes, in order to eliminate induction effects, what I want is pure resistance. In standard laboratory resistance boxes, in standard laboratory resistance boxes, in order to avoid induction effects, in order to eliminate induction effects, coils are wound in the reverse order. Coils are wound in opposite directions. I repeat, in standard laboratory resistance boxes, in standard laboratory resistance boxes, in standard laboratory resistance boxes, in order to eliminate induction effects, in order to eliminate induction effects, comma, coils are wound, W-O-U-N-D, coils are wound in opposite directions. Coils are wound in opposite directions. This is called non-inductive winding. This is called non-inductive winding. 2 more notes to go, then I'll take a break. This is called non-inductive winding. These are all previous questions, okay? Non-inductive winding might come in assertion reason, okay? Non-inductive winding. Fourth one is a question. Show the figure. There are 2 bulbs. One is connected through a resistor, the other through an inductor. Draw the figure. This is a previous board question. Note number 4 is a question. Coils are wound in opposite. I'll repeat one more time for the whole thing. In order to avoid, in order to eliminate the induction effects, comma, coils are wound in opposite directions. Okay. What will happen then? Induction, I'm asking you, induction due to one coil is nullified by the other coil. Induction due to one coil is cancelled by the other coil. Got it? They are in opposite, decoupled, right? They are in opposite directions, right? Negatively coupled. So they'll cancel out. Got it? Got it? Got it? Yes. Magnetic field due to one coil will be cancelled by the other coil. That's it. Okay. Okay. You have a coil like this that is producing magnetism. But if you have another coil in the opposite direction that is also producing magnetism, but they are in opposite direction means they'll cancel out. Oh no. If I have a plus Q coulomb, if I put a minus Q coulomb, what is the net charge? 0. Same way, magnetic fields are being cancelled out. Got it? That's what I said, simple terms. All right. Note number 4, draw the figure. All right, thank you. Arya? Right, note number 4, which bulb will glow? Which bulb glows, turns on? Which bulb turns on and off without any lag? Explain. Which bulb turns on and off without any lag? Without any lag. LAG, without any lag. Explain. Without any lag, explain. Which bulb glows GLOWS without any lag. Explain. Okay. Drawn the figure, right? Correct. I'll explain it. Look at me, please, everyone. What happens when you switch it on? I must have said a billion times now. Tell me, current increases, field increases, flux increases, EMF is developed. That will oppose the cause. Causes growth of current. So the growth is slowed down, right? All these happen where? On the inductor, right? Correct. So on the inductor, there is actually it's being slowed down. That means this bulb will turn on very slowly. Right. See, current is trying to flow, but there is opposition. Where? In the inductor. But does it happen in resistor? No. Resistor, this bulb will turn on spontaneously. This bulb, have you seen that, what you call indicator switch on your TV? When you switch it on, the remote, it turns on very slowly. Have you seen that? No. That's actually an inductive bulb. Let me see if I have it. Let me see. 1 second. I don't know if it's there. Let me see. Not sure whether this is. That's an inductor. This one is an inductor. Okay. When there is an inductor, it always shows some lag. That's actually different, but anyway. Let me see if I have something else. 1 second, just give me 1 second. I have one with me, but I don't have it anymore. I'll show you after break, okay? I'll show you after break anyway. Right. So I'll tell you what happens here. The induction, this coil has what? Current increases, current increasing, field increasing, flux increasing, EMF developed. EMF opposes the cause. The cause is growth of current. So the growth gets delayed. Growth of current gets delayed. Okay. So on this coil, on the SAM, the current grows very slowly. So this bulb turns on very slowly. Correct. How do you explain switching off? Switching off, current decreases, field decreases, flux decreases, EMF is developed, opposes the causes decay of current, right? Correct. So the decay is being opposed. That means decay gets slowed down. So it takes very long time to decay, which means this bulb will take long time to turn on very slowly and long time to turn off. Got it? Whereas the resistor one will have what? No delay at all. The moment you switch it on, it turns on. And the moment you turn it off, it switches off. Got it? Understood? There will be spontaneous response from bulb B1, whereas very delayed response from bulb B2. Understood? Induction always introduces an undecided delay. That is what I said in the previous point. Understood? Understood. I'll show that, next, when you're home, you just see this yourself. When you turn the TV on, the remote, you can see a bulb on the TV, indicator on the red indicator. You haven't seen it at all? What is this? Then switch it off. Then it takes slow. It actually very slowly dies, the bulb, no? But this light, the moment I turn it off, look at this. The moment I turn it off, it's gone. Right. Got it. Spontaneous, right?
Yes.
But on the other hand, if you connect an inductor or capacitor to this, there will be a time delay all the time. Got it? To turn on and turn off. Induction, that is actually induction effect. Got it? Clear? Clear. So you can write here, all of you online understood this? Say yes or no, please. Here, bulb B1, all right, Anthony. Here, the bulb B1, Emma, here the bulb B1 reacts, REACTS. Bulb B1 reacts, REACTS, spontaneously. Bulb B1 reacts spontaneously. Why? Because it is connected to a resistor, right? No induction effects, right? Resistor has no induction effects. Got it? Theoretically, there will be induction effect, but practically there is no induction effect. Got it? Here, bulb B1 reacts spontaneously as there is no induction effect. Here, bulb B1 reacts, REACTS. Here, bulb B1 reacts spontaneously. Spontaneously means without any delay, right? Here, the bulb B1 reacts spontaneously as there is no induction effect. Clear, Kirtana? Leslie, Misha. Here, the bulb B1 reacts. Reacts means turns on or turns off. Got it? Turns on or turns off without any delay. Got it? Got it? Reacts spontaneously as there is no induction effect. But in the case of bulb 2, only 10% of the people responded. Rest of the guys, all of you online understood. In the case of bulb 2, okay. In the case of bulb 2, all right, Jacob. Thank you, Nawal. Bulb 2, in the case of bulb 2, when there is growth or decay of current, growth or decay, when is there growth there? When is there growth? Switching on. When do we have decay? Switching off. Got it? In the case of bulb B2, when there is growth or decay of current, inductance opposes them. Inductance opposes them. In the case of bulb B2, when there is growth or decay of current, inductance opposes them. When there is growth, that is opposed. When there is decay, that is also opposed. That is why we call it inertia of electricity, right? Just now I told you, right? Say something, I'm asking you, right? Okay. So this is why bulb B2 has a time lag. This is why bulb B2 has a time lag. This is why bulb B2 has a time lag in turning on or turning off. This is why bulb B2 has a time lag in turning on or turning off. Okay, so in the case of bulb B1, there is no delay at all. Okay, if you heard me properly, you'll automatically write it. Okay, resistor has no induction effect. So, no delay in growth, no delay in decay. The moment you turn it on, the bulb will glow. The moment you switch it off, the bulb will turn off. Got it? But in the case of inductor, this bulb, there is an inductor. So, when you switch it on, the growth of current will be opposed. So, growth will be very slow. Correct? When you switch it off, decay of current will be opposed. So, the decay also will be very slow. So, current grows very slowly, current decays very slowly. So, that delay will be reflected on the bulb. Got it? The last point before break, note number 5. So, previous question, write this, draw these figures. This is called coaxial winding. Coaxial winding. Coaxial winding. Okay. This is side-by-side winding. That is perpendicular winding. Just write this. How about this one? flux transfer will be maximum, isn't it? Say something, please. Flux transfer will be maximum. That is why we wind coaxially, right? I take an axis, I wind the primary, all of which I wind the secondary. Got it? They are actually tightly packed so that the entire flux of primary gets transferred to secondary. Yes, very good. Right. What about this one? You know, flux will pass, but not all. Maybe like few lines will pass through this, few lines. Not as strong as the first one, right? M2. And what about this one? No flux line will pass through because flux lines here are on x-axis. That one is on y-axis, right? Okay, primary flux has got nothing to do with secondary. What was the board question? Arrange them in the order of mutual inductance. Mutual inductance. Who is the biggest one? M1 is the biggest one, right? Maximum coupled. It is called perfect coupling, tight coupling, 100% coupling, tight coupling. Okay, perfectly coupled. Second one is little less than that, M2. Then third one, it is null, almost zero, loose coupling. There is a term called coupling coefficient which tells you about it, but that is deleted now. Coupling coefficient here is 1. Coupling coefficient here is 0. Coupling coefficient here is in between 0 and 1. Coupling coefficient, it is 1, means 100% coupled. Entire flux of primary moves to secondary. Okay. Coaxial winding, entire flux of primary gets transferred to secondary. That is called coupling coefficient 1. This is coupling coefficient in between 0 and 1, say 0.4, which means it's not as strong as the first one. It's not as weak as the last one. Somewhere in between. Understood? Few flux lines are passing, right? Correct. Side by side winding. And how about the last one? No flux transfer at all. K is equal to 0. Hope you remember this from the video we saw. Now, we saw this, right? Induction radio yesterday, right? For those who missed yesterday, I will show you very quickly. When they are side by side, there will be flux transfer. There will be flux transfer, right? But see what happens when they are perpendicular. The coils are perpendicular. When they come closer, there will be flux transfer. When they are perpendicular, you don't hear sound, right? Why? There is no flux transfer. Got it? Right. Okay. So we'll come back after break. All of you understood this? So there are two more points left. One is the derivation for energy. Actually, it is deleted, but still your teacher teaches it. So I have to take it. I'll be taking it in the next class. It still has a chance to come. Okay. So we have to learn it. Energy stored in an inductor. But now I'm going to tell you about AC generator. All right. You know, you learned this in class 10 also. What is an AC generator? AC generator, you know, from the name itself, it is clear. AC is alternating current. There are two types of current, direct current and alternating current. Direct current. What is direct current? The DC. The one you get from a cell is called direct current. Okay. From a cell, no? This is a cell, right? This remote has a cell inside. And what you get from the cell, what you get from the cell is actually DC, direct current. Okay, on the other hand, whatever the electricity board supplies your home is alternating current. It is a changing current, polarity changing current, about which we will learn in detail in the next chapter. The next chapter is dedicated to alternating currents. Okay. Anyway, this is actually a generator which creates alternating current. What kind of generator? You know, we have hydroelectric power stations in India. Up north, we have Bakaranangal, and down south, we have like Idukki reservoir, or Niagara Falls in US. They have like a reservoir where they store water in a dam. They'll take it down, like I said in the last class, they'll take it down through a pipe called penstock. And then what? That will actually propel a turbine. Turbine is like a fan, huge fan. The turbine will rotate. Okay. So turbine is connected to a shaft which is connected to the AC generator. All right, AC generator. Okay. So AC generator is basically what? It is a coil and a magnet setup. The coil will stay stationary, magnet will rotate. Or the magnet stays stationary, the coil will rotate. All right. Either way, one of them is rotating with respect to the other. Eventually, this will lead to the generation of electricity. Large scale power generation is done by this method. Like I said once, Qatar has a lot of gas. They burn gas. They convert water to steam, and then high pressure steam is propelling the turbine. Okay, the turbine rotates. Again, like I said once, in Netherlands, they have plenty of wind. They use windmills, huge windmills, right? Huge fans, windmills, no? Wind energy? All right. So huge fans or windmills, they are called windmills. They are being rotated using wind. So right at the center, there is an AC generator. All right. So basically, an AC generator converts mechanical energy into electrical energy. That's a previous question. AC generator converts mechanical energy into electrical energy. Mechanical energy into electrical energy. And the components of AC generator are, number one, a huge coil called armature coil. Armature coil. Then there are two, okay, then there is a magnet called field magnet, giant magnet called field magnet. I'll show you a prototype of this in the next class. Okay, small generator I'll show you in the next class. Field magnet. Then there are two rings called slip rings, if you remember what you learned in class 10. And then there are graphite or carbon brushes. Graphite or carbon brushes. These are the components of an AC generator. I repeat one more time. What does an AC generator do? Generator, it generates. Generates what? AC, alternating current. Okay. So it's an AC generator basically generates alternating current. Alternating current, the current that is supplied to your home. Got it? Okay. And that generator has these components. Which are the components? There is a coil, huge coil called armature coil. Armature coil. Then there is a magnet called field magnet. Field magnet, huge magnet. Then slip rings and graphite brushes. These are acting as contacts. I'll tell you what, graphite brushes. These are the parts of an AC generator. And what do you convert here? Mechanical energy is being converted to electrical energy. And I'll show you this. Look at this. I'll show you the diagram for this. Let me just, where was it put? Okay, fine, right. So this is like, this is the biggest generator. Have you heard about Three Gorges Dam? Three Gorges Dam? No. Three Gorges Dam or Hoover Dam? Hoover Dam is in US. Three Gorges is in China. That is one of the largest dams. Three Gorges, I'll show you. Largest dam in the world. You haven't heard about it? Three Gorges Dam. This is the largest dam in the world. Oh. Look at this. The largest dam in the world. It's so huge. Actually, it is believed that the Earth's rotation is affected by the size of this speed of rotation due to the weight that the dam carries. Earth's rotation, speed of rotation has been, it is not proved, but anyway, there is a belief that Earth's rotation speed has been affected by the size of this dam, Three Gorges Dam. And in fact, this is the generator inside the Three Gorges Dam. See the size of a man? Right. So these are people standing there, and size of the armature coil. Armature coil, understood? So armature coil, such huge turbines, these are all turbines. Okay, generators, understood, the coils. And water falls on it, and such turbines are rotating 50 times in a second. Okay, imagine the size. In 1 second, this turbine is rotating 50 times. 50 times in India, 60 times in US, 100 times in Japan. Because in India, we say the frequency is 50 hertz. In Japan, it is 100 hertz, US, it is 60 hertz. It is different in different countries. All right. All the British colonies like us have like 50 hertz. Okay. It's all pre-independent era systems that we have, right? Still. So it's all 50 hertz. Across India, 50 frequency is 50 hertz. Which means, to a common man, what does it mean? Every single generator coil rotates how many times? 50 times in a second. Okay, back in India, you can go inside it. I think I told you once. You have to be on your knees. It's so, actually it's short. And you have to go around the generator, turbine. You can see water falling on it. So scary. Okay, so you can go inside the power station, the generator. And if you kneel, you kneel around this. Understood? And water is coming with such force. The turbines are rotating like 50 times in a second. Got it? All right. And due to the rotation, where does it rotate? The coil is rotating near a magnet. That will create electromagnetic induction. Correct? That will generate electricity, right? Okay, I'll show you something now. That is our largest coil. This is the structure, right? Oh, can you see this? Online guys, can you see this? There are two poles. These are the magnetic poles. These are called field magnets, huge magnets. Right inside, there is an armature coil. Do you see the armature coil? Do you see a coil here? Armature coil, which is connected to two rings. These are rings, slip rings. And then there is a brush, touching brush. They are called graphite brushes. They are acting as contacts to get the electricity out. Got it? Contacts. I'll show you an animation. I think that's better. Okay. Look at this. You will have a better idea. See this?
Hello friends.
Look at this. This is the armature coil. You see this armature coil?
Yes.
See this? And where is it placed? It's placed between two North Pole and South Pole, right? Pole pieces. And this armature coil is rotating. How does it rotate? Right here, you will connect the shaft, at the end of which there will be turbine. Got it? No? See, this is the end of the coil. From the end of the coil, there is a shaft. There is a rod like this. At the end of the rod, there will be a fan-like structure. It is called turbine. Got it? And water hits the turbine rotates, shaft rotates, then the coil rotates. See what happens? When the coil rotates, it is touching the rings, right? Correct. The ring is rotating, right? The ring is touching the brush all the time. Without the brushes, what will happen? If you simply connect wires, the wire gets twisted. Got it. But if you have a ring like this, it is all the time touching the brush. All the time you'll have contact, right? Understood? See, imagine you are taking two wires out of this. Simply two wires out of this, the coil. What will happen? When the coil rotates, the wire gets twisted, right? The wire gets twisted, eventually get broken. Understood? In order to avoid that, look at this. This is what they do. Look at this. They keep a contact here, graphite brush, which is touching all the time. Imagine we have a ring. The ring is rotating. All the time it is touching the brush. So what happens? All the time it has contact, right? Current can come out of it, right? Correct?
Yeah.
See the animation now?
This is how an AC power generator works. A coil is allowed to rotate in a magnetic field.
It's cutting the flux, right? The green lines are flux lines.
As we can see that the bulb is shining as the current passes through this. Now, if we place a galvanometer at this place, so we can see that the current is moving first in one direction, then in another direction.
Opposite directions.
The same will be visualized like this. If you like this, don't forget to...
It's called an alternating current. I'll show you one more thing. Oh.
Hello friends, this is how an AC...
Oh, let's keep it there 1 second. I think I don't have it. No. I'll show it in the next class, okay? I'll show it in the next class, okay? So that's all about the fundamental idea of generator, AC generator, okay? So in an AC generator, what happens? Mechanical energy is converted to electrical energy. Water falls on the turbine, that is mechanical energy. Turbine rotates, the shaft rotates, the coil rotates. Either the coil or the magnet rotates, okay? Either the coil, some countries have coil rotating, some other countries have magnet rotating. Got it? At the beginning of the chapter, I had told you either of them can rotate, right? One is called stator, the other is called rotor. The one which is rotating is called rotor. The one that is stationary is called stator. S-T-A-T-O-R. Stator. Okay, but in India, textbook has said, in India, magnet is rotating. All right. But anyway, that is for operational purposes, operational convenience. Got it? Anyway, basically the idea is this. We have a coil or a magnet rotating in the vicinity of the other. Got it? Coil is rotating around a magnet, or magnet is rotating around a coil. How does it rotate? You can go there and rotate it yourself, but it is very difficult, right? So you let water do the job, right? Okay, water comes in huge amount. If you have plenty of water, then water falls on the turbine. It will actually make it rotate. Got it? Or if you have wind, the wind does the job, right? Or if you have nuclear power plant, nuclear energy, like in Chernobyl, in Russia. Heard about Chernobyl accident? I'll tell you about it later. Okay. Anyway, they use nuclear energy to create heat, fission reaction. Heat. Using heat, they'll convert water to steam. Correct. Boil water to make steam. Okay. Then using steam, they'll propel the turbine. Have you heard about steam engines? Same principle, right? Same like that. Okay. So basically, it is rotated and mechanical energy is converted to electrical energy. What are the components of this? Armature coil, field magnet, slip rings, graphite brushes. Armature coil is like a huge coil. Then field magnet. Field magnet is a giant magnet. In India, I've been to one of the power stations in Idamalaya, right? And that generator, I still remember that turbine had the size of this building. Okay, one turbine. Okay, but that is actually one of the smallest stations in India. Okay, so actual ones, like I said, the Three Gorges or Hoover Dam, you just check it out on Google. All right, the size. Okay, you can't even visualize. So huge. Okay, one small what you call burst of a penstock couple of years back in Kerala actually killed 10 electricity board personnel. Right. Okay, because water is coming in such huge amount, such large amount. Understood? All right. So powerful. Water is so powerful, right? It's coming down from such heights, and then it is making such blades rotate at 50 times in a second. 50 times. Got it? Anyway, mechanical energy is converted to electrical energy. Then I told you the components are armature coil, field magnets, slip rings. Why do we use slip rings? Because this is the wire coming out of coil. We will connect a ring. Why? When this rotates, the ring also will rotate, right? It will always touch the brush, graphite brush. So you will continuously get electricity out of it. Got it? This is armature coil. And the graph also I'll show you. I'll wind up, okay? Look at this. This is the graph. What was that graph called? This is the graph for it. I'll just show you. This is the graph given in the reader. I can't magnify it. Let me see. Magnify. Yeah. See the graph? Look at this. See the graph? The coil is initially perpendicular. That time, the coil is rotating. This is how the coil is kept. I don't know if you'll understand or not. Otherwise, I'll explain the next class. I'm keeping the coil this way, then like this, then like this, then like this, then like this, one full rotation. When the coil completes one rotation, this is what you're going to get. This is what you're going to see. Oh, just give me a second. Look at this. This is the coil. This is the coil. Coil is initially perpendicular, 90 degree, 180 degree, 270 degree, 360 degree. Got it? Which is counted 0. Again 90, 180, 270, 360. 90, 180, 270, 360. How many times? 50 times in a second. Got it? 50 times in a second. So you are getting electricity continuously this way. Continuously this way. I'll show this mathematically in the next class. Okay? That's all. Shall we wind up for the day?